Okay, so nobody actually got to finish these notes in class. If I remember correctly, one class didn't even get to fill anything in. So I was going to do a quick video that went over kind of what to do, a couple of the practice problems, and then the very last problem we're going to go through in detail because you have a problem like that on your homework. So this diagram you've actually seen before. You saw it in Unit 2, and this is something that is called a heating curve. And if you'll remember, we looked at this when we were talking about the different states of matter and phase changes. And we know that we can get a state to change or some matter to change from one state to another by adding or removing heat. So that's how it relates to what we're doing right now. So first, as a review, let's label the graph with our different states of matter. So remember that at a low temperature here, we're starting off with the solid in that first diagonal phase. The second diagonal phase is our liquid, and our last diagonal phase is our gas. And so the horizontal lines, the section 2 and 4, is when we are changing those states of matter. Those are our phase changes. So to go from a solid to a liquid, here describing section 2, that is melting, and to go from the liquid to a gas, that is what we are going to refer to as vaporization. Okay, so the energy needed to increase the temperature for the states of matter. Okay, so the states of matter, again, those are my diagonal sections. You do see temperature changing. So which formula have we been using that involves a change in temperature? Well, it's our Q equals MCAT, MC delta T. So sure enough, in sections 1, 3, and 5, you can use that formula. So for section 1, that solid would be Q equals the mass of the solid. And if we're talking about water, well, the specific heat of solid ice is not the same as liquid water. So for instance, 2.108 would be the specific heat of ice times that change in temperature. And for our liquid water here in section 3, this would be Q equals M times the specific heat of liquid water, which is our 4.184, times delta T. And for our gas over here in 5, this is going to be Q equals M times the specific heat of steam is 1.996 times the change in temperature. So using those formulas with those specific heats, you can calculate how much heat is needed to change the temperature of that substance. But if I need to do a phase change, right, a phase change has no change in temperature. So for those, we're going to be using the moles times the delta H. And again, that can be either H vap or H fuzz. So which one goes where? All right, well, if we're talking about melting, melting is akin to fusion. So this would be the Q equals moles times H fuzz. And the vaporization, well, that obviously tells you that that is Q equals moles times H vap. Now, the difference here is you do need to pay attention that when we are talking about changing temperature for our states of matter, that this M is mass. But when we are talking about changing the state, going from one state of matter to another, that this is in moles. And the reason that this is in moles is because these values are a kilojoule per mole value. So you're going to have to multiply by moles to get the kilojoules. Another thing to note, that since these delta H values are in kilojoules, but the Q equals MCAT normally gives us joules, you are going to have to make sure that you are paying attention to whether or not you are in kilojoules or joules, depending on the question. Okay, and so I did provide these values. These are things that I would always provide on any homework or test, so you've got those. So let's just do a couple of refresher problems here. So for question 1, all right, calculate the energy needed to vaporize. So 15.0 grams of water. So remember, we start with grams, divide by the molar mass, because that's what gives you the ability to use this value, right? So if I've got mole up here, I need mole down here, and 40.67 kilojoules up here. That would be 123 sig figs, and if I multiply that out, that gives me 33.9 kilojoules of heat energy needed to basically turn 15 grams of liquid water into steam. So you can do the next problem on your own, and if you get the correct answer, you would get 1.30 times 10 to the fourth kilojoules, and the reason that is so big is because that is in kilograms. Okay, so which region of our heating curve are we talking about? Well, we're talking about that horizontal section number 4. Okay, next, calculate the mass of water that would be vaporized by 20 kilojoules of energy. So this is just the opposite problem. I'm starting with the 20.0 kilojoules. And if I start with kilojoules, I have to divide by kilojoules. And how did I know that I need 40.67 and not that 6 point whatever? Well, because I was talking about vaporizing. So that's HVAP. 1 mole on top. And in theory, I could leave this here, except it wants the mass of water. So in 1 mole of water, I have 18.02 grams of water, which again is the molar mass. So how many sig figs? 1, 2, 3. So 3 sig figs, that is 8.86 grams of water. And if you did the next two, the correct answers would be 77.5 grams and 0.0598 grams. And the reason that one is so small is because that number is in joules. Okay, so now on to the back of your sheet. And now we've got a couple of other things here. So let's look at this first one. Calculate the energy needed to melt. Well, melt is talking about fusion. All right, so I'm using that H fuzz, which was the 6.03 kilojoules per mole. That's what it says on the front hand side. So 23.0 grams. Grams water. Again, the only thing I can do with grams of water is turn it to moles using my molar mass of water. And if it wants to know about melting that, well, in 1 mole of water requires 6.03 kilojoules of energy to turn it from a solid to a liquid. I have 1, 2, 3 sig figs, so 3 sig figs, that would be 7.70 kilojoules. So if you do the next one, you should get 2,930 kilojoules. And again, the reason that number is so big is because that is in kilograms. And which section are we talking about on my heating curve? Well, it is the first horizontal section, which is section 2. So this is the reverse problem. I want to know how much water I can melt, right? And let's see here, mass of water, that's ice. Water is just the actual name of the compound. So melted is again using my H fuzz. So I'm going to start with the 30.0 kilojoules. If I start with kilojoules, I have to divide by the kilojoules. Have my 1 mole in the numerator. And it wants to know the mass in grams, so I have to use my molar mass in the last step, 18.02 grams. And I have 1, 2, 3 significant figures, so this is going to give me 89.7 grams of water. And if you do the next 2 little problems here, you should get 22.7 grams and 0.397 grams. And again, that last one is so small because that's in joules. Okay, so number 5 mixes them all up, but they're exactly the same kind of problem. So I'm talking about melting, vaporizing, freezing, and vaporizing. Okay, so B and D are using HVAP, and A and C are using HFuzz. So the correct answers for those, for A, it would be 12.0 kilojoules if you do that problem correctly. And for C, if you do it correctly, it'll give you 30.9 kilojoules. For B, this one's annoying because you have to do the 1, 2, 3 sig figs. So here, to get the proper 3 sig fig answer with rounding, it's actually 200 point. That makes both of those zeros significant kilojoules. And then the last one is 30.7 kilojoules. Okay, so it's question number 6 that I want to spend a little bit more time on. All right, so this problem says a 25-gram sample of ice, which is a solid, at negative 10 degrees Celsius, heats up. It melts. Once it melts, that means it is a liquid, and it warms up to 20 degrees Celsius. How much energy is absorbed? Okay, so representing my sections on the heating curve, if I'm starting as solid ice, I'm starting at 1. And then I have to go through melting, and then I'm ending up as a liquid. So if you notice here, as we scroll back up, that is 1, 2, 3 separate problems, right? I have to use this formula, and this formula. Okay, so on your homework, you actually are going to have a 5 portion, but we'll just start it off with 3. So I've got 3 different things, and here's how you want to look at that. So first off, and it's helpful to just write it all out. So first off, in section 1, I am taking a solid from a negative 10.0 to what temperature? 0, because that's when melting occurs. And then in step 2, I am just melting. I'm staying at 0 degrees. And in step 3, I am taking a liquid from 0 to 20 degrees Celsius. So those are my 3 separate problems. Okay, so I've got 25 grams for all of them. So let's do step 1, my solid. So I'm using Q equals M times my specific heat for ice is different. It is 2.108 joules per gram degrees Celsius times that delta T. So what values do I know? Well, my mass is 25.0. I have my specific heat, and my change in temperature, well, my final is 0 minus a negative 10. Okay, 0 minus the negative 10 is actually a positive 10. So if I have a positive 10 times 2.108 times 25.0, how many sig figs should I have in that answer? Well, it is 3, and that gives me 527 joules. Okay, so let me switch colors here. So for the melting implies H fuzz, so Q equals moles times H fuzz. Well, that would be then my 25.00 grams. I have to convert that to moles. And then I want to multiply that by my H fuzz, which was 6.03 kilojoules. Okay, so how many sig figs there? Well, again, it's still 3 because of the 6.03. So to 3 sig figs, that would be 8.37 kilojoules. And lastly, my liquid water. So this is going to be Q equals M times my specific heat for water, 4.184, times delta T. My mass is still 25.00 times 4.184, but now my change in temperature, I am final temperature of 20. My initial is 0. So 25 times 4.184 times 20 to 123 sig figs gives me 2,090 joules. Okay, so the question wants to know how much energy is being absorbed. Well, I've got 3 different numbers, right? This one, and this one. And to know how much total is absorbed, I have to add them together. But I need to do something first, because you should notice that only the melting temperature here, or energy, is in kilojoules, whereas both of these other values are in joules. They have to all be in the same unit. So we typically put everything in kilojoules. So for this first value, 527 joules, to turn it into kilojoules, I would move my decimal 3 times to the left, so that is 0.527 kilojoules. And for my last value here, 3 places to the left, would be 2.09 kilojoules. Now I can add all those together. So I'm going to do it this way. So it's been a minute since we've done addition rules for sig figs. But if we stack them this way, it makes it very obvious. 2.09. Okay. So if I add these together, drop my 7, 2 and 7 is 9, 9 and 9 is 18, carry the 1, so 9, 10. Okay, so where do I cut off for sig figs here? It is to the least number of decimal places, which is here. That 7 makes me round up, and my final answer would be 10.99 kilojoules of energy is needed to take 25 grams of negative 10 degree ice, warm it up, melt it, warm it up to 20 degrees liquid water.